On Friday, we talked about the property of equality for exponential equations. And you might recall from Friday's lesson that when we had like bases on both sides of the equal sign, relatively speaking, they undid each other. So you could just set the exponents equal to each other. Well, our goal, like I said, for this section is twofold. On Friday, we took some time to solve for x in exponential equations, but today we're going to take some time. I'm going to teach you how to solve for x in logarithmic equations. So that's the skill you're going to leave with today. How do you solve for x, if there's a log hanging out in your problem? And just like we have this property of equality for exponential equations, likewise we have a property of equality for logarithmic equations, and it works in pretty much the exact same manner. Basically, we have if b, x, and y are positive numbers where b can't be 1, then log base b of x is equal to log base b of y. These two things are allowed to be equal to each other if and only if x is the same as y. In other words, it's like logs of the same base on both sides of the equal sign undo each other. And they give us a numeric example to go off of. It says if log base 3 of x is the same as log base 3 of 8, like this log base 3 on both sides never happens, so x has to be equal to 8. Conversely, it'll be true that if x is equal to 8, then log base 3 of x will be the same as log base 3 of 8. So you're going to see two types of equations today. Give you a little preview of coming attractions. You're going to see problems where there are multiple logs in a problem. And you're going to see problems where there's just a single log in the problem. Multiple logs and single logs. That's what you're kind of contending with today in class. And our overall goal is to solve for x, to figure out what is the value of x in each of those problems. And in example 3, it starts off rather straightforward because it's directly referring to the property we just talked about. In part A, it says log base 7 of 6x minus 16 is equal to log base 7 of x minus 1. Well, if you have log base 7 on both sides of the equal sign, it's kind of like that whole thing never happened. So these undo each other because the bases were the same. Essentially, we get 6x minus 16 is now equal to x minus 1. And then we just solve for x. We have a linear equation. I usually move all of my variables to one side and constants to the other. So I would subtract x from both sides. So you get 5x minus 16 equals negative 1. Add 16 to both sides. So x in this problem has to be equal to 3. It is important to always check your solutions to logarithmic equations. That comes up kind of in a big way in a little bit. Remember, you're never allowed to take the log of a negative number. If you try to do it in your calculator, it's going to give you an error. It's going to say it's a non-real answer. So we just have to check to make sure that we're not taking the log of any negative number when we go to solve our equation. So if you take a look here, we have x equals 3. If I plug 3 into both sides of the equal sign, I end up taking, what, log base 7 of 2 on both sides. Those two things are equal to each other, so this solution does work. All right, part B. That one's all yours. I'm going to ask you a question, though, before you get all into it. I just want to review with you, because believe it or not, we are coming up on a final exam here in about, 2 months. So exciting. There are currently 3 situations where you have to check for an extraneous solution. You just got one of them today. Logarithmic equations, you're always going to have to check to make sure that you don't have an extraneous solution. Does anybody remember the other 2? Where we had to go back and check? Okay, Danny. No, solving quadratics, we didn't have to check so much. It was a good idea to check, but we didn't have to. Well, is that what you were going to say? Daniela. Absolutely, yes. Absolute value equations you always have to check. Very good. That came up on your midterm in a pretty big way. A couple of you missed that one. So watch out. Absolute values you must check. One more. Radical equations. There's a square root in it. You got to check to make sure that you're not taking the square root of a negative number. That's a big deal. You actually get 4 total in this class. So you just got your third one today. You're going to always have to check for x in your logarithmic equations. Make sure you don't get an extraneous solution there. So you got 3 out of the 4. You get your last one in chapter 8 when we go to solve for rationals. We'll cross that bridge when we get there. All right, so part B is, like I said, all yours. Looks like you finished it while we were chatting. Anybody feel comfortable in sharing their response? Good, Will. Yeah. So you checked it. It works. Questions for Will? All right. So next up, in example 4, we are asked to use the exponential form of a logarithm to solve each equation. I'm actually going to show you 2 ways to take care of this problem. I'm going to follow the directions for one, and then in part B, I'm going to do the problem in a slightly different way. So you might recall from Friday's lesson, we'll backtrack for a sec. You might recall for Friday's lesson, when we were asked to solve an exponential equation, we ended up quite frequently just taking a logarithm of both sides. However, when we get a logarithmic equation, do you see the method they're kind of referencing here? They want us to write it in exponential form. So it's this whole idea of those inverse operations undoing each other. A log undoes an exponent, an exponential equation undoes a logarithmic. So here what we can do is actually use our log cycle to help us solve for x. You can write this logarithm in exponential form to isolate the variable. So here's how that looks. Basically what we're saying right now is 5 squared is actually equal to 3x minus 8. That's what they mean by writing it in exponential form. Use your log cycle. So 5 squared is 25, and that's equal to 3x minus 8. And then, you know, we solve all of our linear equations by moving our variables to one side and constants to the other. So I'm going to go ahead and move my constants around a little bit. Using the addition property of equality, I can add 8 to both sides. And then 25 plus 8 is 33. Balancing my equation here, I have 3x left over on the right side. And then I can use my division property of equality to divide both sides by 3. I get x equals 11 for that problem there. And then I go back and I just check. 3 times 11 is 33, take away 8 is 25, and then, hey, yeah, log 5, 25 is totally 2. So it does work. Are there any questions on part A before I go on? So I use the log cycle there. In part B, I'm going to use a different technique, however. If I want to get rid of this log base 4, you can also exponentiate, which is a technique that they use a little more, I think, in your pre-calc and your calculus classes. Does anybody remember what that word means? We'll give you a break, Will. You're doing great. What's that word mean? What's its root word? Danny. Yeah. So, quite literally, it means take your whole problem, lift it up, and make it an exponent. So what we're going to do is use this as our base, because I'm trying to undo log base 4. So the base on both sides is going to be 4. To exponentiate just means to lift the entire problem up and make it an exponent. So now that I have a base of 4 for my, base of my exponent, and then a log base 4, we know that those things undo each other. So the 5x minus 1 falls down. And then we have 4 to the 3rd power on the right side. That's 64. So now I have a real simple linear equation. Ryan, you're looking at this very critically. Do you have a question? No? Okay. You remember, you don't write it down unless you understand it. Questions about that? I just lifted the whole problem up and made it a big old exponent. Then I add 1 to both sides. Divide both sides by 5. X equals 13. Questions about that? Oh, I gotta sneeze. So now you have 2 tools. You could use the log cycle, or you could just lift the entire problem up and make it an exponent. It's kind of up to you, whichever way you like better. All right, last type of problem you're going to see, where there's multiple logs in the problem, and you might try to isolate them, get one by itself, but it doesn't seem to work. Even if you subtracted log x minus 1 from both sides, it's not really going to get rid of the log. It's not like these base 10s are going to go away. So when you see multiple logs in a problem, step 1, condense them into a single logarithm by using your properties from 7.5 from last week. So this is why I had to teach section 7.5. We got to use our log properties to condense our logarithm. So again, step 1 is to write the problem as a single logarithm. So that left side of the equal sign, I'm going to condense those 2 logarithms down to 1 logarithm. I see a plus sign in between. Can anybody tell me if I should use the product, quotient, or power property? What do you think, Victoria? Product, very good. When you see a plus sign, you're going to multiply those things together like that. So we have log 5x times x minus 1, and that's equal to 2. Remember that if there is no base, it's automatically a base 10 logarithm. That's our common log. That was one of our vocabulary terms last week. So step 2 is to eliminate the log. And you have 2 tools from the previous slides. You could exponentiate both sides, or you could use the log cycle to get rid of that log, essentially writing it in exponential form. So you can pick whichever one you like. I think for this one, since I'm crunched in on space, I'm going to use my log cycle. So I know that 10 squared in this problem is going to be equal to 5x times x minus 1. The last step in solving a logarithmic equation is to solve and check. You must remember to check for extraneous solutions. Super important. So right now I have 10 squared equals 5x times the quantity of x minus 1. I know that 10 squared is 100, so I'm going to swap that out. And because I see the product of a couple of x's right here, I know that this is going to be a degree 2 or quadratic on the right side. So I really can't solve for x unless I get one side equal to 0. So I know that if I distribute that 5x in, I get 5x squared minus 5x. And again, because I have multiple x's right there, I have to get one side equal to 0 before I solve. So this is going to look like this. Subtract 100 from both sides using my subtraction property of equality there. Then I have to factor this. First thing I see, the first method you should always try in any good factoring problem is the GCF method. I do see a greatest common factor of 5. And then I can factor that resulting trinomial pretty easily with a little guess and check. You could use whatever method for factoring you're comfortable with. If you like AC grouping, you can use that. But when I factor it, I get 5 times the quantity of x minus 4 times the quantity of x plus 4. All of these 3 things are supposed to multiply together to give me 0 back out. Well, that means that one of these 2 things right here must be 0. So I use my 0 product property to solve for x. That means x minus 5 has to be 0, or x plus 4 could be 0. Add 5 to both sides, and subtract 4 from both sides. Initially, we get 2 solutions. But as I look, thinking about, I can't take the log of a negative number, I know that negative 4 isn't going to work out for me. Because if I plug it back in, if I take my negative 4 and I plug it back in up here, I end up taking log negative 20. So if you, open your calculator real quick, and just to show you I'm not full of baloney with this part, you open up your calculator and you type in log negative 20 in an effort to kind of check, right? And you get an error. So we know that that answer can't work. What's up, Bree? The properties can only be used if you're talking about those big numbers being positive. We're not allowed to say oh yeah, but if you multiply these together, it would make a positive. No, because you can't use the properties unless all of those values are positive. You're always plugging it back into the original equation. That's why that's important. You don't want to plug it in somewhere in the middle because it'll work then. This one doesn't actually work. Those properties only get to be used if you have a positive value. All right, are there any other questions? Let's do a couple more together. Make sure you get the hang of it. For instance, part B. So here's our 3-step approach to solving for x in a logarithmic equation. Part B. Step 1, we're supposed to write with a single logarithm. Well, hey, that only says log 1 time, so that step doesn't need to be done. Step 2, you have to get rid of the log. In this case, I see log base 4. And just for giggles, this time around, instead of using the log cycle, I'm going to exponentiate. In other words, this base of 4 right here, I'm going to make a big 4 on both sides of the equal sign there, essentially raising my entire problem up to, as Danny said it, make it an exponent. So this log base 4 and this 4 here kind of cancel each other off. And you get 10x plus 624 equals 4 to the 5th, which I think is about 1,024. So then we get 10x equals 400. And I'm into step 2 already. Step 3 even. I'm solving for x right now. Divide both sides by 10. Lop off some zeros there, like this one and that one. We get x equals 40. So then you do have to check to make sure you didn't force out any negative values for your logarithm. 10 times 40 is 400 plus 624 is 1024, and that is 4 to the 5th power. So this guy totally does work when I plug it back into the original equation. Are questions about that? No? All right. I want you to try these two. See how it goes. Write it as a single log first. And then step 2. You get rid of the log. And then step 3, solve and check. Go ahead and give you a minute to do that. I think I am going to do the honors just a little bit to finish up C and D. So if you look at part C, again, I run through my steps. So I have to think back, well, how can I condense these two things into a single logarithm? So as I take a look at part C right here, see this plus sign? That lets me know that I have to use the product property. In other words, I have to take the product of 2x and x minus 5 to try to write these as a single log. So essentially, here's how that's going to look. It's going to be log 2x times x minus 5. And now that left side is a single logarithm. And then this is still equal to 2 on the right side there. After I write it as a single logarithm, using the properties we talked about last week, I am going to go ahead and get rid of log. Remember, there is a base associated with log if it's not written. This is called the common logarithm or the base 10 logarithm. You could exponentiate both sides, but as I got a quick glance of a couple papers, it seems like this class really likes the log cycle. So you could take this logarithmic equation and write it as an exponential equation. Remember, day one on logarithms with just those two things are the same. You know, they're just rewritten versions of each other. So we could do 10 to the second power equals 2x times x minus 5. And then 10 squared is 100. And this becomes 2x squared minus 10x on the right side. Again, because of that x squared, I can't solve that unless one side is equal to 0. So this is going to be rewritten as 2x squared minus 10x minus 100 equals 0. And then I do see a GCF hanging out in there. So 0 is going to be equal to 2 times x squared minus 5x minus 50. And then little guess and check. Factors of negative 50 that make negative 5 would be negative 10 and positive 5. I use my zero product property to set x minus 10 equal to 0 and x plus 5 equal to 0. Add 10 to both sides, subtract 5 from both sides. I know tentatively speaking my two answers are 10 and negative 5, but upon further review, I plug in negative 5 and I'm like, oh man, that makes me take a log of a negative number. So that guy doesn't work. The final answer to this problem is 10. For part D, very similar except it was base 6 this time around. I do know, and it happens a lot on your homework assignment tonight, this symbol in between is a plus. So to do step 1, more common than not, you have to use your product property. So this means that we're going to go ahead and take log base 6 of x times x minus 9. We just multiply these two things together. And on the right side, that is still equal to 2. After I write as a single log, I always eliminate the log. And just to show you a variety of techniques, you could do the log cycle or you could exponentiate. Just because I have this space, I'll exponentiate. Log base 6 and a base of 6 undo each other. So on the left side, I can bring down my x times x minus 9. And then this is equal to 6 squared, which evaluates to 36. Again, I'm going to have to distribute. And I see once again that I have x squared or a degree 2 polynomial, and I really can't solve that unless one side is equal to 0. Unless you wanted to complete the square, which we could talk about another day. Factors of negative 36 that make negative 9. 9 and 4. Nope. What is it? 18 and no. Thank you. I was like, what am I missing? 18. So yeah, you get two answers, 12 and negative 3. Totally spaced out there, my apologies. And then, so yeah, you would go ahead and look at these two answers, tentatively speaking, check them. And it does look like this negative one isn't going to work out because it makes us take the log of a negative number, and we can't do that. I was trying to make 5 with factors of 36, but it clearly says 9 in between. Okay, questions about our lesson today? All right, so you could, for tonight's assignment, it's basically just a continuation of what you did last night. Remember to check your odds in the back of the book. I'm really contemplating doing accuracy tomorrow. So please make sure you're checking your answers in the back of the book. That is super important. But yeah, it's just a continuation. You could actually do it on the same paper. So just keep going where you left off. You start with 25, and I think you go to 40, 43 odd. Let me double check that for you. Yep, 43 odd.